Now let's move on to the third algorithm under embedded type feature selection, which is ElasticNet. ElasticNet is an embedded type feature selection algorithm that combines the L1 lasso and L2 ridge regularization techniques. It is used for selecting relevant features and performing regression analysis in situations where there are many correlated features. So let's begin with the definition and explanation of it. So elastic net is a linear regression model that adds both L1 and L2 regularization penalties to the loss function. The L1 penalty encourages sparsity by driving some feature coefficients to exactly zero, effectively performing feature selection. The L2 penalty encourages small coefficient values, helping to reduce overfitting. So, the combination of these two penalties provides a balance between a feature selection and regularization. So now let's look into the applicability. So elastic net can be commonly used in situations where there are a large number of features, especially when these features are highly correlated. Now it's time to look into the mathematical equation or formula. The objective function of elastic net can be defined as the sum of residual sum of squares plus alpha times L1 penalty plus beta times L2 penalty, where the first portion that you see here is the RSS, residual sum of squares, or you can also say it as RSS can be represented as the sum of squared residuals. Then we have the L1 penalty. This portion is L1 penalty. L1 penalty is the L1 regularization term, also known as lasso penalty, and is calculated as the absolute. This one is calculated as the absolute sum of the coefficients multiplied by a tuning parameter alpha. So this is our tuning parameter, and this one is nothing but the absolute sum of the coefficients multiplied by by a tuning parameter alpha. And similarly, just note down that point. It's the absolute sum of the coefficients multiplied by the tuning parameter, because it's not squared up. It's not squared up, so that's why you have to include an absolute a modulus symbol. Then we have beta times L2 penalty. So L2 penalty is the L2 regularization term, is also known as ridge penalty, and is calculated as the sum of squared coefficients multiplied by the tuning parameter beta. So alpha and beta are the regularization parameters that control the strength of the L1 and L2 penalties respectively. As we have discussed earlier, this portion L1 and L2 regularization penalties to the loss function. So the L1 penalty that you can see mxi plus z. So this one encourages sparsity by driving some feature coefficients to exactly zero. So that's what it's gonna do. So if it is, if the coefficient are bigger, that can be handled. But when it comes to if if you have a small coefficient values, then it's difficult to handle the things. Then comes the square of the square penalty term. So the L2 penalty term, which is a ridge one, encourages small coefficient values, helping to reduce overfitting. So the combination of these two penalties, that is L1 and L2, provides a balance between feature selection and regularization. So now let's look into the algorithm working process. Okay, so anyway, so our elastic net regression is equal to lasso regression plus ridge regression. So now, if you want to look into the algorithm working process, so first step is to initialize the elastic net model with appropriate values of alpha and beta. Then fit the model on the training data using the fit method. The third step is during the training process, the model optimizes the coefficients by minimizing the loss function, which includes the RSS, residual sum of squares, and the regularization penalties. Then we will move on to the fourth step. The model selects the relevant features by driving some coefficients to zero through the L1 regularization. L1 regularization, and the fifth step is to evaluate the performance of the model using suitable evaluation metrics such as the mean squared error, MSE, or R squared. Okay, so now let's look into some of the uh, applications of this, or some of the fields where elastic net is widely used. So the first one, elastic net is widely used in various fields, including predictive modeling. So predictive modeling, it can be used to select relevant features and build regression models for predicting outcomes such as house prices, stock prices, or customer churn. Then we have the bioinformatics. So elastic net is applied in gene expression analysis to select relevant genes to contribute to specific biological outcomes or diseases. Then image analysis, it can be used for feature selection and classification tasks in computer vision applications too. So now let's look into the some of the real life activities that we can handle using the elastic net. The first one is, as usual, the same application or the same real life example, which is predicting house prices based on features like square footage, location, a number of rooms, and other relevant factors. Then we will move on to the second example here, identifying important genes or biomarkers, or predicting biomarkers for predicting the progression of a disease based on gene expression data. Then next one, analyzing the customer data to identify key factors that contribute to customer satisfaction or churn in a telecommunications company. So overall, ElasticNet is a versatile algorithm that combines the advantages of L1 and L2 regularization, allowing for effective feature selection and model regularization.